In this video, we are going to be going through the first few steps of analyzing and designing a rigid mat foundation. So these first few steps are part of what's called the rigid mat foundation design procedure, or sometimes called the conventional procedure for design of mat foundations. And all of this is more on the structural engineering side. So this topic, if you're exposed to it in a course, this is very much a topic that would be covered in like a second semester foundation design course, or maybe a second semester reinforced concrete design course. So the purpose of this video is to just give you the brief introduction and first few steps of the process. This video does not illustrate all of the steps of structural design of rigid mat foundations, just the first few steps to get the ball rolling for someone trying to do this. So let's take a look at a plan view of this foundation we have here. So we're looking down on this foundation and we see that we have 12 columns here. And each column is supporting a different axial compressive load. The corner columns, as you see here, four corners are experiencing 50 kips. The edge columns around the perimeter are holding up 60 kips, and then the center two columns are holding 80 kips. We see a close-up view of a cross-section of a column. It's a 2 foot by 2 foot column, so 24 inches by 24 inches. And then in the long direction, which I'm going to label, I'm going to put some, axes here: north, south, east, and west. In the east-west direction, we see that columns are spaced 40 feet on center, and the north-south direction, the columns are spaced 30 feet on center. So one thing to be careful about is, because they're spaced on center with these dimension lines, you need to note that the distance from the center of the corner columns to the edge is going to be half of the width of the column. So got to be careful with that. That's going to indicate that the entire dimension line in the east-west direction is actually not 120 feet. It would be 122 feet. And then in a similar way, in the north-south direction, the total length of the mat is 62 feet, not 60 feet. Okay, so the first thing you want to do, I've already written out parts of this solution ahead of time. So some of it I'm just going to talk you through, and other parts I'll show some calculations in the video. The first thing you want to do is you want to calculate the soil pressure under the entire foundation. Now, this is kind of like an average. So what you're doing is you're going to say the sum of all of the column loads divided by the area of the mat. Now, first comment, sum of all of the column loads, that's not really the dead load of the building. I mean, instinctively you may say, well, that's just the dead load of the building, but not really. Remember, if you're doing structural design here, these column loads should already be factored using LRFD. So the sum of the column loads is really the sum of the factored column loads that already have LRFD factors built into them, and each of these column loads is already based on a critical LRFD load combination. So it's not really the weight of the building, it's more than that, because you factored in other things, maybe live load, maybe rain, etc. So it's the sum of all these column loads divided by the total area of the mat. And when we sum that up, we get 720 kips divided by 62 times 122 pounds, okay? And then when we get that, calculate that, we get 95.2 PSF. I just went ahead and converted to PSF to make sure that doesn't look like 0.122. It's 122 feet. All right, so you get a number that's a stress value or a pressure value. So I went ahead and put it in PSF. Now, one thing to keep in mind, if you notice the directions say draw the shear and moment diagrams for the central strip ABCD. So the way this procedure works for rigid foundations is you can consider one strip of the foundation in each of the primary directions. So in this particular example, what we're interested in is what we're calling the central strip of this foundation, which is going to be something like this. That's going to include columns A, B, C, D. Okay, now what's cool about this is once you analyze the most critical strip, which if you have a nice symmetrical problem like we do here, that's going to be the strip with the columns that have the most loads, thereby the central strip in this case. Once you design that for all the reinforcement, then you can take what you've designed for that central strip and then just repeat that same reinforcement scheme for the edge strips on either side of it. Okay, now in the actual design procedure, you want to do this for both primary directions. So if you were doing a full-blown mat foundation design, you would take the most critical strip in the east-west direction, analyze it, design it, repeat that design for the adjacent strips, which sometimes are called the edge strips in the east-west direction. Then you would repeat that process in the north-south direction. So you would take one of the central strips in the north-south direction, analyze it, design it, and then take that design and repeat it for all of the rest of the strips in the north-south direction. But again, this short video is just meant to illustrate the first step, and I'm only gonna show the central strip A, B, C, D, which is in the east-west direction for the purpose of this video. So once you've gotten that load, the soil pressure, we got 95.2 PSF. Remember, that pressure is under the entire foundation, and that means it's also specifically underneath our strip of interest. So here's what I'm going to do. I'm going to consider the width of the strip to be a tributary width, okay? So check out what I'm going to do. If I know my column spacing in the north-south direction is 30 feet on center, then that means the tributary width for that middle strip ABCD is, you guessed it, it's 30 feet total. It's 15 feet going on either side of that strip, okay? So I'm going to go ahead and draw that out. Okay, so we've drawn this out, and this is the strip that we're interested in. And again, we're looking at 15 feet on both sides of that column line, okay? And again, that's based on a tributary width. So here, I'm going to try to sketch in here my 4 columns. Now, when you're doing this in a more of a real scenario, you want to draw this to scale as best as you can. Obviously, my artwork is not the most beautiful and not the most to scale, but you want to draw this to scale, okay? And let's put some nice dimension lines on here. So remember, we're going center line of these columns. So these are the 40-foot dimensions, and don't forget you do have a 1-foot dimension from the center of the edge columns to the edge of the mat, okay? And pushing up beneath this strip is that 95.2 PSF. Now, here's where we have to be careful, okay? This procedure does not account for what's called shear force between adjacent strips, okay? So when we separate a mat out into different strips, there's technically going to be this kind of discontinuity between adjacent strips where you're essentially neglecting shear force, okay? And because of that, you have to make some adjustments to your pressure calculations. Otherwise, your shear and moment diagrams won't close properly, okay? So I'm going to take you through a couple of quick steps to do that. So the first thing we're going to do is we're going to compute what's called the total soil reaction beneath the strip that we're interested in, okay? And I'm going to call that P sub R. And we're going to say P sub R is equal to Q sub T that we just calculated times the tributary width times the length of the strip, okay? And that's why we're saying 95.2 PSF times 30 feet times 122 feet. And when you punch all that through and you convert to kips, you get 348.4 kips. And again, that's called the total soil reaction beneath the strip, okay? Then what you need to do is you need to compute what's called the average load on the strip, okay? So what you do is you take that total soil reaction piece of R that we just got, and you add that to the column loads on the strip of interest, and you divide it by 2. So what you're doing is you're taking you're taking kind of an average between two things. One thing is the total soil reaction between the strip, and the second thing is the sum of the column loads on the strip. So it's treated as two separate things that you're adding together. Now, the sum of the column loads, of course, is however many columns you have there, but that's the reason why we divide by 2 and we don't divide by a different number, because it's really treated as an average between two entities, okay? And so when we do that, I get 314.2 kips here, okay? Now, from these numbers, we're going to compute what's called the modified soil reaction for the strip. Again, this all goes back to the idea of in a full problem, you're not actually capturing what would happen between adjacent strips. So you have to make modifications to the strip you're analyzing. So to compute this modified soil reaction, I'm going to call it Q mod, okay? And I'm going to say it's equal to the total soil reaction, which we calculated several steps earlier, times the average load divided by the soil reaction beneath the strip of interest. And so all three of these values we already have. 95.2 PSF is Q total. Average load, 314.2 kips. We just calculated that right in our previous step. And then P sub R is that total soil reaction between the strip a couple of steps above us. And we get this, what's called modified soil reaction for that particular strip. And that's equal to, in our case, about 86 PSF. That's 85.9 PSF. Okay. Now, the next thing we need to do is compute what's called a column load modification factor, okay? Now, we're going to use this factor and we're going to multiply each of our actual column loads by this number. And we're going to get this number by saying the average load that we calculated a few steps above, that's 314.2 kips, divided by the sum of the column loads on that strip. Okay, so that's 60 plus 60 plus 80 plus 80, all in the denominator. When you punch that through for our problem, you get 1.12. And again, I want to emphasize why we're doing this, because it seems a little silly. Why are we doing all these calculations? But the reason why is when you're analyzing this and you're looking at a strip, you're not capturing what is happening in the vicinity where adjacent strips are touching each other, okay? And specifically in regards to shear force. So in order to have a static equivalent system where the shear diagram closes properly and then the moment diagram closes properly, you have to adjust some of these values, and you're taking things that are happening on the whole slab and you're adjusting them for the strip of interest. So that's what these steps are doing for us, okay? So we say next, apply that factor, that column load modification factor, to each column on the strip. So what I did for the column load at A, I said 60 kips times 1.12, and that's how I got the 67.3 kips as the modified load on column A. And then I did that for all four of the columns on that strip. Okay, so now the next thing we're going to do is we're going to draw the equivalent system for that strip. Okay, so here's what this is going to look like. We're going to draw a profile view of it. So here's the mat. Here's the mat. And here's going to be some pressure underneath it, and I'm gonna kind of ask you what you think this is in just a second. Let's call it W. Okay, we're gonna give it a new name, and I'm gonna go ahead and put the column loads here. There was column A, so we're gonna call that this is 67.3 kips, and then column D over here was also 67.3 kips. These are modified loads on here. And then we're going to have 90 kips at column B. And then 90 kips at column C, okay? And remember where our dimension lines are. Our dimension lines are center to center on the column. So these are 40 feet, 40 feet, 40 feet. And don't forget that little half column width of 1 foot on both sides. Okay. Now let's go back to this distributed load W. This W is going to be an equivalent uniform line load. Okay. So that's what's going to end up helping us be in static equilibrium. So what do you think this is going to be equal to? It's a line load. So you got to be careful. It's not in PSF, it's in PLF. Okay. So here's what it's going to be equal to. It's going to be equal to Q modified, so the 85.9 PSF times the tributary width. Okay. So this is going to be equal to Q mod times the tributary width. Okay, so that's the 85.9 PSF times 30 feet, and let's punch that through. $85.9 times 30 feet. So I get, if I go to KLF, I get 2.577 KLF. Or you can get 2,577 PLF, but it's a line load, not an area load, okay? So it's kips per foot. All right, so check this out. This system, because we've made proper adjustments and we've taken things that are happening on the entire slab and we've adjusted it to distribute things properly on one strip, this system should be in static equilibrium. So we're not really having to solve for any reactions per se here. We're ready to go right into the shear force diagram. So we're going to say shear diagram. So I'm going to go ahead and I'm going to draw my axes for the shear diagram. This is going to be X in feet and V in kips. And we're going to move left to right and look at this system and draw this diagram, okay? So starting all the way at the left side, remember you have a half width right here, because remember the column load is applied at the center of the column. So you have a 1 foot width of a little distributed load on either side of this mat going up. So check out what I'm going to do. That distributed load is the 2.577 KLF, and it's distributed over 1 foot going up. So guess what's going to happen? We're going to jump up. We're going to jump up by an amount equal to 2.577 KLF times 1 foot. Okay, and that's going to be over this little 1 foot distance. So right here, I'm going to say 2.577. All right, wrote that backwards, 2.577 kips. And that's a linear increase right there, okay? And then we're going to say minus 67.3 kips, okay? And when we do that, we're going to jump down. We're going to jump way down here to negative 64.7 kips, okay? And then we encounter a 40-foot spread, that's right here, center to center, 40-foot spread of the 2.577 KLF, pointing up. So we say plus 2.577 times 40 feet, and that'll take us to a positive 38.4. So when we do that, we're going to, at the center line of the next column, we're going to be right around here at a positive 38.4, and that's going to be a linear increase. And then, of course, we encounter the 90 kips pointing down, so we say minus 90, and that's going to jump us back down to a value equal to about negative 51.6, okay? And then what do we encounter next? Well, we encounter the next 40-foot spread of 2.577 KLF. So we're at negative 51.6, so we're going to say plus 2.577 times 40 feet. And guess what? That's going to linearly increase us up to a value of about 51.4. Okay, there we go. And then we hit that column load minus 90, and that's going to jump us back down to a value of about negative 38.6. So that's about here, negative 38.6. And then we hit another 40-foot distributed load piece. So we're going to say plus 2.577 times 40 feet. And that puts me back up to a positive 64.5. So that's going to be about right here, 64.5. And then we hit the last column load minus 67.3, which will shoot me down to a negative 2.78. And then guess what? We still have that 1 foot overhang right here. So we're going to say plus 1 foot times 2.577. And that closes nearly to 0. It should theoretically close to exactly 0, but due to some round off error, it may not exactly close to 0. So this should be kind of like anti-symmetrical with respect to itself. So we can shade all of this shear diagram. And what you're going to do is you're going to use these shear values, so long as they were properly factored with LRFD factors very early from the column loads. You're going to use these shear values to do your shear design of the slab when you're designing the reinforcement. So these are the shears you're basically going to be using when you're doing one-way and two-way shear design calcs for the reinforcement. Now, what about the moment diagram? Well, let's draw that real quickly. Moment diagram. Now, the moment diagram for a system like this is going to be quadratic, right? Because the shear diagram is linear everywhere. So we're going to have a moment diagram in kip feet. Here's our x value in feet. And again, we got to be careful with our dimension lines here, okay? So we're gonna what you're gonna have to do is use similar triangles in a few spots, obviously. So this first dimension line right here is 1 foot, and then the dimension line on the shear diagram from point to point, you're gonna call this maybe x, and then you'll call this other dimension 40 minus x, okay? And or maybe call it x1 just to give it a different name. So let's do our similar triangle calculations. We'll say x1 over 64.7 equals 40 minus x1 over 38.4. So when we get that dimension x, let's see what it ends up being. 38.4 divided by 64.7 plus 1, 40 divided by that. So I get x1 is 25.1 feet, and of course 40 minus x1 is 14.9 feet, okay? And you're gonna do a similar kind of thing on each of these other domains. So let's do that together. I'm doing this in real time with you right now. So on this next domain, I'm looking at this nice looking triangle right here. We're gonna have maybe x2 and then 40 minus x2. It'd probably be pretty smooth sailing to do this in Excel and be a little quicker for these similar triangles. So x2 over 51.6 equals 40 minus x2 over 51.4. Now, theoretically, that should be equal. So really, because of our symmetry we've got going, if we punch this through, we should get x2 equals 20 feet. And, of course, 40 minus x2 should also be 20 feet. And then also due to the anti-symmetry of this entire system, this dimension right here should be 14.9 feet, and then this dimension right here should be 25.1 feet. So you can recognize attributes of symmetry and anti-symmetry. So now let's get the moment diagram. Be very careful with your positive and negative areas. So I'm going to start with this little bitty triangle on the left. So 1/2 base times height, 1/2 times 2.577 times 1 foot gets me a positive 1.29. Okay, so I'm going to come up right here, and that's an increasing linear function on the shear diagram, even though it's very small. So that means it's going to be a concave up quadratic segment. Okay, then next triangle. Let's look at this big triangle right here. All right, we got see 1/2. I need to write the value here, 1.29. Okay, so then we have a big negative triangle. So minus 1/2 base times height. So 1/2 times 64.7 times 25.1 feet from our similar triangles. That brings me down to a big negative 811 kip feet. Okay, a big negative 811 kip feet. So that's gonna, again, this is a linear increasing shear diagram. So this is gonna swing us down, concave up. Down here, it's actually more specifically 810.7 kip feet. And then we're gonna swing back up by this positive area right here. So plus 1/2 times 38.4 times 14.9 feet. So I'm gonna swing up some to a value of negative 524.6. Negative 524.6. Okay, and then we've got another negative area. I'm going to move my label for this over here just to kind of get it out of the way. We got another negative area, so we're going to say minus 1/2 times 51.6 times 20 feet. So that's going to swing me back down again. It's going to be concave up still. It's going to be swinging me down symmetrically, technically, to a negative 1041 kip feet. And then it's going to swing me back up by the same area, so plus 1/2 times 51.4 feet times 20 feet. Again, that theoretically should be symmetrical in that middle span due to the symmetry of our column loading. So right here is negative 524.6 again. Okay, maybe a little round off in there. And then we're going to have minus 1/2 times 38.6 times 14.9 feet. I'm looking at this little area right here now. So that's gonna put us down. Oops. Try to redraw that. That's going to put us down here again to about negative 813 kip feet. And then we're going to swing back up with this big positive area. So that's going to be plus 1/2 times 64.5 times 25.1 feet. So that's going to swing us back up really far. Oh, I think I punched something in wrong. Plus 1/2 times 7 times 25.1. Yeah, so it should swing you up just barely above the x-axis at about 1.3 kip feet, and then you've got that last little bitty area. Oops, didn't mean to erase that. You got that last little bitty area over 1 foot width that curves you back down to 0. So this should be our moment diagram, which looks a little odd. It does look a little odd, but all of these are concave up parabolic segments that correspond with linear increasing shear segments. And notice that we have a lot of negative moment here. We have a lot of negative bending in this particular example, which is very possible based on our column spacing and our magnitudes of our column loads. So from the moment diagram, you would use these values to calculate your flexural reinforcement. These are the MU values you use to calculate the flexural reinforcement. So I know it looks a little odd. I'll be honest, I just made this example up, so it's very possible that the numbers are not the most practical numbers, but this is the general process, and so it's probably pretty smoother to do these calcs, quote, by hand, and then in a report, like if you're doing something for senior project, then you just manually type in some of the governing equations and then draw the figures in the report. You could use Excel for this, although to draw the shear and moment diagrams in Excel, that may be more work than just doing it by hand like we just did. So that's up to you.